Hello to everyone. We are from Group 2, consisting of Darshana, me, Divya, EILEEN, and Jasmine. We present about Experiment 6, which is Borden Tube Pressure Gauge, which is an open-ended experiment. Firstly, it's the report summary. So as for the introduction, the pressure intensity at any point in static or moving fluid can be measured using various types of pressure measuring instrument. Borden tube is one of equipment to measure pressure. Borden tube pressure gauge are most widely used nowadays because of their reliability, compactness, low cost, and ease of use. It consists of a curved tube of elliptical cross-section bent into a circular. Before any measurement system or equipment to be used, it is compulsory to calibrate the equipment. So the equipment can just as accurate as the working standard. Calibration means checking the pressure gauge reading against a very accurate device. One of the calibration device that is available in our lab is the so-called dead weight tester. To calibrate a measurement system, you have to compare its input with a standard known input. To compare its output with a standard known input. Next. In this experiment 6, we have to calibrate the Borden tube pressure gauge by mounting the transducer in a closed vessel with a piston at one end called a dead weight tester. The weight testers provided were in various standard weights. We need to study the Borden tube principles and any related information as much as possible prior, prior to the experiment. Students are expected to compare experimental results with the theoretical ones in the calibration of Borden gauge pressure. It is required to figure out the error occur during the experiment in order to calibrate the gauge pressure. As for the objectives, there are two main objectives, which is calibrate a Borden tube pressure gauge using dead weights and to determine the gauge error. So these are the apparatus. The three main apparatus is Borden tube pressure gauge, dead weight tester, and 1 kg piston. So as for the report summary, the aim of this experiment is to perform pressure calibration on a Borden tube pressure gauge using a dead weight tester. This experiment is done by inserting piston into the cylinder and air bubbles inside is removed by rotating or push the piston. When piston is inserted into the cylinder, the pressure gauge deflects as the first reading. Then load weights are added slowly until total mass reached 6 kg. Procedures are repeated for increasing and decreasing weights load for 2 times. Experiment is conducted successfully as true pressure, which is the standard known input, is almost the same as the pressure recorded, which is output. The input reading is the weight on the piston produces a known pressure in the vessel equals to the weight divided by the piston area, while for the output reading can be obtained from the pressure gauge. I will pass to the next present.
So for the theory, as the fluid pressure enters the Borden tube, it tries to be reformed, and because of a free tip available, this action causes the tip to travel in free space, and the tube unwinds. These simultaneous actions of bending and tension due to the internal pressure make a non-linear movement of the free tip. This travel is suitable guided and amplified for the measurement of the internal pressure. But the main requirement of the device is that Whenever the same whenever the same pressure is applied, the movement of the tip should be the same, and on withdrawal the tip should return uh, of the pressure on the tip should return to the initial point. So when the pressure is applied to the tube, it tends to straighten out, and the deflection of the end of the tube is communicated through a system of levers to a recording pointer. This gauge is widely used for steam and compressed gases. The pressure indicated is the difference between the system pressure and to the external ambient pressure, and is usually referred to as the gauge pressure. So due to the change in stiffness of the internal components, calibration must be carried out to get accurate reading of pressure. Calibration means checking the pressure gauge reading against a very accurate device. That way tester is figure 2 showing the dead weight tester. This deadweight pressure gauge calibrator consists of a precision machine piston and cylinder assembly mounted on leveling screws. The weight supplied are added to the upper end of the piston rod, which is rotated to minimize friction effects. So the measured pressure can be obtained from the reading of the Borden tube pressure gauge. And the theoretical pressure in the cylinder can be calculated by using equation which as follows, where F is the force added to the weight tester in kPa, and A is the cross-sectional area in meter square. And by working out the theoretical results, we can also work out gauge error, which is the percentage error, by using the equation which as follows. Percentage error equals to theoretical value minus experimental value over theoretical value and times 100. I'll pass on to the next presenter.
The next one is the procedure. First, the piston is put into the cylinder. Then the piston is rotated to ensure all the air bubbles are removed from the tube. While there is no dead weight on the top of the piston, the reading shown on the pressure gauge is recorded as a first reading. After that, a first dead weight around 0.5 kg is put on the piston top, and the reading shown on the pressure gauge is recorded as second reading. Then the weight is increased by adding on one dead weight on the piston top. The reading shown on the pressure gauge is recorded as third reading. The reading of pressure gauge is kept recording by adding on dead weights until a total of 5 kg mass is obtained. The experiment is repeated 3 times to obtain the average reading. All dead weights are removed from the piston top, and the piston is removed from the cylinder at the end of the experiment.
Okay, for the raw data analysis, where firstly we need to find the mass of piston, which is constant 1 kg, and then the cross section area of piston, which is in meter square, and then the true pressure exerted by piston is calculated using mass of the piston times the gravitational acceleration over cross section area of piston in unit of kilonewton per meter square. And then the true pressure exerted by total mass is calculated by multiplying the total mass, which is the weight and weight added with the piston weight, and then multiply with the 9.81, which is the gravitational acceleration over the cross section area of piston in unit of kilonewton per meter squared. Next, this is the table that used to collect the data experiment, where the mass of mass is the mass of piston, and then these are the formulas used to calculate the pressure, percentage of error, and the others are to collect the data. I will pass to the next presenter.
Hello, I will be discussing about the results and discussion. So you can see here that mass has been added 0.5 kg at a time, and then the pressure reading was collected. The pressure reading was collected 3 times for both loading and unloading, just to get the average pressure value, and then towards the end to get the percentage error. The true pressure is minused off with the pressure we calculated divided by the true pressure times 100%. This will further be discussed on the next slide. Next. Okay, so A, theoretical pressure. In order to... Okay, I think the slide behind. Okay, theoretical pressure. In order to calculate the pressure, the definition of pressure is used. The formula is shown below, where P is pressure, F is force in newtons, M is mass in kilograms, A is cross-sectional area of the plunger in square meters, and G is gravitational acceleration in meters per second squared. The resulting unit of this calculation is 1 kilonewton per square meter. The measured pressure is measured experimental pressure, which can be obtained from the reading of the Bourdon tube pressure gauge. Next. Okay, here I've listed down the percentage error based on the loading and unloading from 0 kg mass added to a total of 5 kg mass added. Next. Okay, so percentage error can be calculated like that, which is your measured pressure minus theoretical pressure over theoretical pressure times 100%. So from the observation based on the table from the previous slide, the error is significantly higher when no weights are present on the platform, which could indicate problems with the piston inlet such as restricted motion or poor lubrication. The error varies midway through the weight trials, which could be symptomatic of mechanical fatigue. In the case of mechanical fatigue, the Bourdon tube would be a possible failing element. Next. Next, I'll be discussing source of errors and methods to minimize said errors. So the first error is when weight is added, the dead weight pressure gauge calibrator responds slowly to the change in pressure and hysteresis, which may induce friction. So a method to overcome this error is rotate piston in an attempt to remove air bubbles inside the cylinder tube and to reduce friction so that more accurate pressure reading can be obtained. The next error is the division of scale reading of the dead weight pressure gauge calibrator is too wide. Reading might not be most accurate. A method to solve this is that scale reading should be more sensitive. The third error is parallax error. Parallax error is bound to happen when taking reading of pressure. The position of eyes are not perpendicular to the scale of Bourdon tube pressure gauge. Method to overcome this error is experiment should be carried out several times to obtain an average value. The reading should also be taken by several people. Next. The final error is apparatus is sensitive to shocks and vibration caused by surroundings. For example, if a member were to accidentally bump into the table while experiment is conducted, movement of table influences the reading. A method to overcome this problem is members should be more cautious when experiment is being carried out and not move about too much. Experiment should be repeated several times to get a more accurate reading. Next. So I'll discuss about repeatability and accuracy of this equipment. So A, repeatability. It is a measure of how consistently the pressure gauge is in accurately repeating the same measurement if all conditions remain the same. So for example, if exposed to the same pressure on two separate occasions, the gauge would show the same PSI if all ambient factors, for example, pressure, temperature, remains the same. B is accuracy, and is a measure of how effectively a pressure gauge is in repeating the upscale reading on the downscale cycle if all conditions are to be remain the same. So for example, while a pressure gauge may read correctly at 0, midpoint and full scale during the pressure up cycle, it may read too high at the midpoint check during the pressure down cycle, while still correctly returning to 0. This stretch that is visible towards the middle of the scale during depressurization is called hysteresis, an inherent trait of an elastic element that hinders its ability to repeat the upscale performance on the way back down. I'll pass to the next presenter.
The next is the conclusion. So according to the experiment, we can conclude that boundary pressure gauge is the one of suitable instrument to measure the pressure, but the readings are not accurate as the actual value. The readings which are recorded from the experiment are closer to the actual value. The errors such as parallel error can be avoided and minimized by ensuring our eyes are perpendicular to the measurement scale, which is pressure gauge, when taking the readings. The random and systematic error also will occur in this experiment, and hence, in order to overcome these errors, we need to repeat the experiment about 3 times to get an accurate value. The last one is the reference. That's all from us. Thank you.